Hi, my name is Yemin Tang. I'm a rising senior in electrical engineering. The project I've been working this summer is called Development and Characterization of Inkjet Printing for Wafer Bonding and Sealing of Integrated Microsystems. My advisor is Professor Najafi and Dr. Becky Peterson, and I work closely with one of the graduate students, Ali. So this project is mainly about MEMS packaging and involves developing new sealing technologies for a miniature gas micropump. My goal is to deposit sealing materials such as epoxies, which is a kind of glue, onto substrates like PDMS or glass, and identify the appropriate sealant. And then I have to develop the printing technique of the Dymatics inkjet printer. And finally, I have to test the effectiveness of the new sealing methods. First of all, a little bit of background information. What is MEMS and MEMS packaging? MEMS stands for Micro Electro-Mechanical Systems. It is the integration of mechanical elements, sensors, actuators, and electronics on a common silicon substrate. And it uses microfabrication technology. Then what is MEMS packaging? MEMS packaging is used to integrate different components of a MEMS systems. And it provides mechanical support, protection from the environment, and electrical connection of the whole system. In this project, I had to seal the top and bottom of the PDMS polymer at certain position and channel of the gas micropump to provide certain function of the pump. The channel width, which I must print into, is 150 microns. And the precision I need to achieve is within 10 microns. The method we use here is inkjet printing. That may sound like familiar to you because we use inkjet printer in our home and office. But the scale here is much smaller. The working principle is that the piezoelectronic deforms when applied certain voltage, and the displacement caused by the PTZ results in the drops being ejected. So here are some benefits of inkjet printing in MEMS. It has high resolution, which means we can have very small drops. And the size can be adjusted by the size of the nozzles, voltage, and other parameters, which is really good. And there's no specific tooling such as photo masks or screens needed. What's more important is that we can get a diversity of materials and print it. Like in bioMEMS, bioactive fluids such as DNA, protein cannot be possibly be suitable for photolithography, may be well compatible with inkjet printing. We see here the picture on the left is the working stage of an inkjet printer. There are many parameters we can control, and with the control of these parameters, I get quite good printing quality. We can see the two pictures, the difference of the two pictures on the right. Here are some performance specifications I get after I adjust the number of nozzles used, improve the alignment accuracy, and optimize voltage applied to a single nozzle. I also optimize the temperature and purge cycle during printing. I'm able to get a very clear and size-controlled pattern, use the model fluid and the glue. Here are some scanning electronic microscope image of my printing. With these images, I was able to accurately measure the dimension and geometry of my printing. The testing process is going on. I make some inspection, and I use the machine to test the shear strength and leak permeability, and finally the thermal durability. So to wrap up a little bit, my summer research experience has been really rewarding. I learned to do a lot of literature review. I read those theses and publications and make summary. I got familiar with the inkjet printer and scanning electronic microscope, which may help my future research, I believe. I also get to see many state-of-art facilities within the lab. I learn to measure, record, and analyze data. I attend a lot of the meetings and seminars about what's going on, learn about what's going on in the MEMS field. So that's pretty much it. Thank you for your attention.